this module 15. Look at the module page. Here I have two documents. Maybe very quickly, can I explain to you what these type of questions are, and hopefully you can practice on these problems. Don't know whether I have answers to these or not, right? But at least these are some questions you can practice, right? So this first question, this is univariate. This first question is in a study of high school student health behavior, a random sample of 500 high school children was surveyed. In this random sample, 212 responded they did not wash their hands. And I want to construct a 95% confidence interval estimate to estimate the percent of high school students in the sample population who did not wash their hands. So what kind of question is this? You see this 95% confidence interval, that means what? This is confidence interval problem. Okay. Now do you remember what kind of formula you should use? Okay. Now SPSS doesn't have an option for this. So if you do see this, this is a situation that you have to do the use the confidence interval estimate formula. Let me do this. So let me bring up the okay. Let me make sure. Microphone. Can you hear me? Are we doing okay? Can you hear me? Mike, if you can hear me, could you wave your hand? Okay, good, okay, good. So that one, you know, let me see. Part A, okay. So part A, that's an interval estimate for proportion. So the formula is what? This one, if you recall. Okay, you know what p hat is, right? That's a sample proportion out of the, let me see if I can drag it down, out of the 500. Okay, 212 responded that did not wash their hands. And sample size is 500, right? And then you have a z-score for 95% is 1.96. You should have that memorized. So during the exam, you don't have to bother to check the table. Okay. So that's the part A. Part B, how large sample is required? Okay. I think we went through these questions before, right? Part B is the sample size and sample size formula. We wish to estimate the sample size. We did not wash it. How large sample is required, right? Remember the formula was like Z over B, the Z alpha over 2, square time P hat, 1 minus P hat. If you do have the proportion information given, you can use that for this P hat.
Dr. Chang, can you move up your paper? Thank you.
Okay, the Z alpha 95% is this, and beta and B is the marginal error, right? Marginal error is given here 4%, so this is 4%, 0.04, right? But anyway, that's a formula, all right? And part C is a situation that there's no prior information that's given. Oh, I'm sorry. Actually, part B is a question that there's no prior information. I missed the parenthesis there to explain. Here, part C say, believe the percentage is 40%, right? So for that one, you will use the same this formula. Okay, my apology. Okay, for B, the proportion is not given. Okay, So when proportion is not given, you should use a formula like this. Time 0.25. I want you to remember that formula, right? If you don't know the proportion, this one is assume that proportion is 0.4, right? It's given, then you can fill in that information. If proportion not given, use 0.25 for this part, right? So this is sample size question related to interval estimation. Okay. I think you know this pretty well, right? We did that in the second exam, right? Then the next one is one sample question related to quantitative measurement, right? So it is about estimation of mean when you have quantitative variables. So how do you do the confidence interval estimate for mean? Okay. And then the second one is if you do the confidence interval estimate mean, how large a sample size will be needed if you want your marginal error within 2. Okay. So that number 2, the confidence interval estimate, actually sample size, sample mean, plus or minus some t-score, standard deviation over square root, and that's a formula, but SPSS can do this for you. You can either use this one or use SPSS. SPSS is probably the easiest since you have the data, right? Part B is sample size problem for confidence interval. So that's the alpha over 2 times sigma over marginal error squared, if you recall. So that's this formula you should use, right? I'm not going to go through this detail for you because I wish I can cover a few more things for you, right? But pointing to you exactly what formula you should use, okay? Then number 3, which test should be used, right? We want to test whether the average limb body mass of this population is less than 32. So we talk about testing average, testing mean. And we have a sample size this small, definitely the t-test, unless normality is not good, right? So actually part A is what? One sample t-test. So you should do a one sample t-test. And you can use SPSS to do this. Okay. Hopefully you practice how to use SPSS to do this. Right? So part B is checking for normality assumption. You run normality test, you see the SIG on the Shapiro-Wilks is 0.729, so you know normality is okay. Okay, p-value is so high. Then you should then be able to state the hypothesis. So what's a null and alternate hypothesis? You need to know how to state those, right? And what's the value of test statistic? We can get it from SPSS, right? So this is a t-test, one sample t-test, okay? I guess the C is stating hypothesis, right? And D is about t-test statistic. You should be able to figure it out, all right, from the software. E is about decision rule, and remember decision rule always the same. You reject null hypothesis if p-value is less than alpha. Okay. C, D, E, F. Draw a conclusion. All right. So number 3 should be easy. You shouldn't have problem with that, right? Otherwise, you can go back to my lecture video, right, and review that, or even look at the SPSS instruction for one sample t-test, right? I think the one that most of you have problem is this number 4, question 4, which is the sample size related to hypothesis testing for mean. Okay, this one, part A, want to find the sample size so that people can have 90% power to reject null hypothesis. New treatment can actually reduce cholesterol by 10 on average. And the standard deviation for cholesterol level for the population is around 20, right? So this is actually one-sided test, right? I mean different. There's any difference. So that's that's actually one-sided test. The first one is one-sided test. Second one is actually, let me see, reject null hypothesis. The treatment actually reduce cholesterol by 10, right? So that's one-sided test. When it's about reduce. If you want to say the mean, the reduction is different, right? Or there's the mean is different, right? Or the cholesterol, average cholesterol level is different, either higher or lower, right? Then that's two-sided test, right? But anyway, if there is a one-sided test, the sample size will be z of alpha plus z of beta time standard deviation over the effect size, difference you like to test, and square. Alpha will be 0.05, that's given. Beta from this question be 0.1. Why is that? Because that 90% power is 1 minus beta, right? So you know that 0.9 is 1 minus beta, so beta is 0.1, okay? So that you can get the z alpha 0.05 plus 0.1.
Dr. Chang, we can't see what you're writing.
Yeah, sorry about it. Okay, over there. Times sigma. Sigma is given, let me see. Let me see if sigma is given. Let me see. $20, right? Sigma is 20, standard deviation 20. So this is 20 and the effect size 10, right? You want to see whether the difference is 10, okay? And this whole thing square. 0.05 is 1.645. 0.1 is actually 1.28 if you look up the bottom row of the T table. Right? So for the exam, you should bring your maybe T table. Remember the bottom row of the T table, right? Is for these special Z score. Okay. So that you can finish that, right? For one-sided test is that. For two-sided test, this formula is n equal to z alpha over 2 plus z beta times sigma over the effect size, the difference that you wish to test, and square that, right? And again, the difference you want to test is 10, right? New treatment can actually affect the cholesterol level by 10 on average. And it says a two-sided test, right? So that's why you need a z alpha over 2. And z alpha 2 is 1.96, right? 0.1 is 1.28. This thing times 10, 20, right? Standard deviation 20 over the size you wish to test is 10 and square it, okay? And generally, once you found a number, you want to round up, right, to the next higher integer, and that's your sample size, okay? So this is actually a one sample. Oh, let me just hold it here in case you haven't got it. Right. Let me see. Oops. Okay. So you got to use your calculator to figure this out, right? This happened again. Okay. And I think we have questions like that in the previous exam too. Okay. Then let's look at another document. Is that all? Let me see. That's it. All right, for this one. This is kind of reviewing the exam too, right? Let's go back to this one. So then if you click the second one, we probably have gone over this one too. This is two sample tests or pair sample test. If you read the question. This is a pair sample test, right? So this is important. Right? Students often make mistake in the question like this. Don't know whether it's a pair sample or two independent sample. So if you use the wrong test, then that whole question, you got that whole question wrong. Okay. So you have to be careful. Whenever you see that you have a pair of observation come from same subject, or the two observations, they are related, right? This is a BMI before, this is BMI after. They're both from subject 1. That's a pair sample situation. Okay. So we have pair sample, the way you analyze the data will be different. When you have pair sample, what you would do is find the pair differences, right? Let's say your difference is before minus after, okay, then this one will be 1, and this one will be 0, and this one will be 4, this one will be 0 again, then you have a 4, and 1, and the 2. Okay, so if you want to test whether there's a significant difference between before and after your test, you need to test whether the average of these differences is significantly different from 0 or not. Okay. So the question here, a BMI score from a random sample to record both before and after dive. Use the following data to test whether there's a reduction of BMI. Okay, so if it asks whether there's a reduction of BMI, it is suggesting that before is greater than after, and that's what you want to test, right? So your null hypothesis, no reduction, right? And the alternative is has reduction. You can write it in words, right? Or some people would say the mean of difference is 0. Or you say mean of difference is, depends on whether you use before minus after or minus after minus before. If you define your difference before minus after, then you're talking about mean of difference is what? Greater than 0. That's your alternative hypothesis, and that's what you want to test. Okay, so this one, whether there's a reduction or not, that's actually, reduction means what? The mean of the difference in this case is greater than 0, so this will be a one-sided test. Okay, so this will be almost like one sample t-test on these differences. Okay, make sense? Hopefully you can continue and finish this problem, right? Now this will be different. You have two populations, okay? And we want to see these two populations. You take one sample from each of those populations. Each sample has 7 subjects. So if you look at these data, they are exactly the same. I just made it up, all right? So I can create another situation that I have actually 2 different populations. Maybe this is female population, this is male population, right? Or maybe this is the white population, this is black population, right? So 2 independent sample from different populations. If this is the case, this is a 2 independent sample test. So you got to do the 2 independent sample t-test. Okay, let me call this SPSS. Let me show you how to use SPS. So let's kind of quick review how to use SPS to solve these problems. Okay. Hope I have connected campus. Yeah. Okay. Let's look at this one. Maybe let me just do the first one too. All right. Let's do the first one too. I have these. I hope I can copy and paste. Can I? Oh, great. And copy these. Wonderful. Okay. So this is before. This is after. So if I do have before and after, I can do transform compute to generate a difference variable. I call it DIF. And that's before minus after. Okay, I can just double click and then, or you can just type this expression. If you know exactly what the variable name, right? Minus after, leave space in between variable name and the operator. Okay, click OK. Go back to the data sheet. You kept that. You have that differences. Okay, and this is actually remember pair sample t-test is really one sample t-test on the differences. So we can do the analyze, compare mean, one sample t-test on that differences. All right, testing with the differences. This thing is actually whether difference is greater than 0 or not. If there's a reduction, means average of the difference is greater than 0. Okay. But anyway, SPS is only do two-sided tests, but we can convert it to one-sided test. So I click OK. I get these results. T statistic is 2.66 and p-value is 0.037. Okay. Now this T statistic, or if you look at the original statistic here, the mean difference is 1.7. So it's greater than 0. And that is supporting our alternative hypothesis, in favor of alternative hypothesis. Okay. In this situation, the t-test statistic reads this number, right? T-test is T is 2.661, right? But important thing is what the p-value. What is the p-value? The two-sided test p-value is 0.037, but we are having one-sided test, and this is right-sided test. P-value should be area to the right of this statistic, okay? But p-value to the right of that multiplied by 2 is 0.037, so this is 0.037 divided by 2, so that is 0.01, almost 9, right? And that's a p-value which is less than 0.05. So you will reject the null hypothesis. Null is no different, support the alternative that the reduction is significantly greater than 0. Do you remember this? I hope you remember this. Okay. So you can draw a conclusion. Of course, I skip a step. That is, when you do things like this, sample size small, you have to test for normality, right? And when you're testing them for normality, that's testing normality on this data, the differences, right? So if I go back to my data, if I want to test for normality, I click Analyze, Descriptive, Explore, and exploring this difference variable, okay? And do a plot, normality plot with tests for that. If you click OK, you get the p-value for that, and it's 0.119, so it's greater than 0.05, so normality is good. Okay, so in this example, I can show you two things, right? It's a pair sample test, right? It's actually a pair sample situation, but we're actually doing a one sample test, testing whether the average difference is greater than 0 or not. So I kind of doing two things, one sample t-test and pair sample t-test. Okay. Now, if you want to do this problem to be different, you have two independent populations. So in this situation, you want to see whether there's anything different between the mean of the two populations. It is two independent sample t-tests. Okay. So for this situation, you actually you have 14 subjects. Each subject you make one observation. So to create this data, let me create a new data. All right. This data should be, I come here. Oops. Just select these. And select these. And then create another variable indicating which group it is. Right? So I have two samples, sample 1 and sample 2. So you see the way you create data be different. For two independent sample tests, right, you actually have BMI measurement. You also have another variable that is group, right, population. So you have a population variable. You also have BMI variable. Okay. And there's normality assumption for things like this. You want to check whether each of these population are normally distributed or not based on their sample. So you can click Analyze, Descriptive Explorer, put the BMI there, population as a factor, so you can do normality tests for each group of BMI, right? So you click Plot, normality test with plus, and click OK. To help you to check normality. Both are greater than 0.05, so normality assumption is okay. That's necessary assumption for this test, right? Then you click Analyze, compare means, independent sample t-test, put the BMI, you want to test for BMI, comparing these two groups, right? Now you click Define Group to put in the two group values. I use 1 and 2, so I just put 1 and 2 as those group IDs, right? Click Continue. If I click OK, it'll do a two-sided test for testing signal indifference, right? This number under SIG is test for equality of variance, if you remember. Then you have this p-value, right, for testing whether they're signal different in means. And they're both greater than 0.05, so different is statistically insignificant at 5% level. If you want to do one-sided test, then probably the difference will be significant, right? Because you're going to divide this by 2, or divide it by 2, subtract from 1, depends on whether you're doing a left-sided or right-sided test. Okay. So that's actually two independent sample t-tests. Okay. Then the following question is actually a 3 sample. So when you do have 3 samples, you want to see whether these 3 population where these 3 samples were from, the mean of them are significantly different from each other or not. All right. That's an extension of two independent sample tests. Let me create that file. Let me new data. And to create that file, the format should be similar. The way you do that very similar to two independent sample tests. You just continue putting these data in one column. Okay. And putting group ID. So you got all the data in. This one is group or population. This one is, what am I doing? BMI. Okay. So you have BMI variable and group variable. Okay. So that's actually, if you remember that diagram, I want to see a diagram. That's this situation. Okay. You have categorical variable more than 2 category, and you have actually, I'm sorry, this one. And your response variable is quantitative, and you have more than 2 category, all right? You have only 2 category, you have 2 independent sample tests, which is what we just did. Okay, but anyway, let's go back to the SPSS. So for this thing, again, you can check for normality. You do it similar to what you did earlier for 2 independent sample tests. besides putting BMI as dependent, you also put in group as a factor list and do the plot and normality plot with test and continue and OK. You can check the normality assumption for all three. And they're all greater than 0.05, so normality is good. Okay. Then you can run this. Will be Anova. Compare mean and one-way Anova. It'll give you a test that will test whether there's a difference among these means, right? So dependent is the BMI group is your factor. You just click OK. It'll do the one-way Anova. If you want to do pair comparison, you would click on this post hoc button and check on whatever multiple comparison method you like to do. Okay. And click continue. And then click OK. And you'll be able to get the Anova test p-value here is 0.000, very small. This is a p-value we'll use to conclude the test, right? The null hypothesis will be there's no difference in mean, right, of these three populations. The alternative is at least a pair of means, the difference is significant, right? So when you do this problem, null hypothesis, no significant difference in population means, right? And alternatives, significant difference exists for at least a pair of means. Or there's significant difference between at least a pair of means, right? Okay, the alternative hypothesis is not that all three means are different from each other. That's not, all right? It could be that population 1 and population 2 is different, significant, but population 1 and 3 are not significantly different from each other, right? So only at least a pair of mean, right, different significant. That's the alternative, okay? What's a test statistic? Test statistic is this F statistic. P-value is this one, okay? The p-value is so small, that means you're going to reject the null hypothesis. Okay. So this is one-way Anova. This is something that we just did. Right? You also did an assignment on that. And then you can look at this multiple comparison too. It can help you to compare group by group. Right? There are three groups, so you can make three comparisons. Group 1 and Group 2, the p-value, the difference is not significant because p-value is 1.84. It's greater than 0.05. Compare Group 1 and Group 3, p-value is so small, less than 0.05, so Group 1 and Group 3 difference is significant. Right? Here, Group 2, Group 1, Group 2, Group 3. Right? So Group 2, Group 3 difference is also significant. Group 1, Group 3 difference is significant. But between 1 and 2, difference is not significant. Okay? So you can see them from this table. Right? And this actually gives you a homogeneous subset to tell you that 1 and 2 stick difference is not significant. 3 separate from this group. Okay, so there are actually 2 subgroups from this 3 populations. Okay, I hope that makes sense. And all these 3 tests, right? Pair sample test, 2 independent sample tests, or one-way Anova. These are all parametric tests. You use a t-test or f-test, okay? Now, what if you did the normality test and you found that normality is not good? Then you would have to do the non-parametric, and that's what we learned last time. All right, how do you do non-parametric? I think the following questions about this one is this is one sample test, right? Then it repeat all these example again. We did this. Let's go back to the first data. The pair sample. So if this pair sample, you want to test whether there is a significant reduction, right? You have before and after. Okay, so if you want to do pair sample test, you can click and Non-Parametric. If you recall, you click Analyze, Non-Parametric Test, Lexi dialog. You can actually do. It depends on how you set up your data. You have a pair of data. You can actually do the two related sample tests. Right? Click on that. Especially if you want to test whether there's a difference. Right? You're not testing whether a difference is significantly different from a certain non-zero value. Then you can go ahead and use that. And you can, the first variable, generally the pair difference is using variable 2 minus variable 1. So if you want to do the same analysis as what I did earlier, you can put the after in first and then before next, right? So variable 2 is before, variable 1 is after, then it'll use before minus after, right, to do the test. And you have a Wilcoxon check. That means you're doing the Wilcoxon sign rank test, right? Make sure you remember when you write your note, make sure you write these name of these tests. This is called Wilcoxon. It shows Wilcoxon, but you should write down Wilcoxon sign rank test. Remember, you use sign and also rank of the observation. I click OK. You get the result from the test. Okay. There's no negative rank. All the rank are positive. That means what? Every measurement, actually, there are 2 ties, right? So out of 7 observations, there's no negative rank. There's no negative measurement. There are 5 positive measurements. And so positive means what? Before, greater, and after, right? If before, greater, and after, that means what? Your evidence supporting there's reduction, okay? And then you saw a p-value two-tailed test is 0.0241. This is for two-sided tests, okay? Now, if you want to do one-sided tests, you either divide this by 2 or divide this by 2, subtract from 1. But remember, how do you decide what to do? You always look at the evidence, whether the evidence is in favor of your alternative hypothesis. What's our alternative hypothesis? Here we want to test whether there's a reduction, right? Or mostly before, greater, and after, right? If there's a reduction, before should be greater than after. After would be less than before, right? So your evidence really supporting that. If that's the case, the p-value should be half of the two-sided test p-value. That rule always the same, right? When we do one sample t-test, the situation is the same. If you look at the evidence, your evidence is in favor of your alternative, then you would divide the two-sided test p-value by 2 to get the one-sided test p-value. Okay. Of course, if I want to test whether there's a difference, right, before and after there's a difference, whether the difference is negative or positive, it doesn't matter, then you're doing the two-sided test. This will be p-value already. Okay. So for the paired sample, the data has to be arranged like this, right? Non-parametric alternative for this is so-called a sign rank test. Okay, Wilcoxon sign rank test. Now the next question is this one, two independent sample again. We want to do non-parametric one, right? The non-parametric two independent sample test is called Wilcoxon rank sum test. It is also developed by Wilcoxon, but it's Wilcoxon rank sum test. It's rank sum for one of the sample, usually is the first sample. Okay, so the way we do it, let me look at the second data. This is the way you set up two independent sample problem, right? You have BMI, you also have the population identification variable. Then what you do is click Analyze, Non-Parametric. Again, I always like the legacy dialog. This is independent, two independent sample, right? So click two independent sample. And you're testing BMI, and a group variable is your population. It's just putting their population ID that you use for these different variable, different groups. Continue. And Mann-Whitney is checked. Remember, Mann-Whitney is the same as Wilcoxon, right? So this is Mann-Whitney U statistic or Wilcoxon rank sum test. They are the same thing, okay? So if you click OK, as soon as it give you the output for it, The average rank from 1 is 9.57, from 2 is 5.43. So the first group BMI is greater than the second group, so their average rank is higher. Okay. And if you look at the p-value, they're both great. This is asymptotic. Remember, there's an asymptotic one. This is approximation when you have large sample. And there's also exact p-value, that's 0.73. But both of them are greater than 0.05. So if your goal is to test whether there's significant difference between these two populations in terms of BMI, there's no significant difference at 5% level. Okay. But if you're doing one-sided test, testing whether the population 1 is greater than population 2, then your evidence really supporting that statement, right? Actually, population 1 has higher average rank than population 2. And if you really want to test the BMI from population 1 is greater than population 2, if that's your alternative hypothesis, then the p-value would be half of that, right? Because your evidence is in favor of that alternative hypothesis. Okay. So this is a non-parametric version of that. Okay. When do you use that? When you try to do two independent sample t-tests, but you find out that the normality tests fail, your data does not support normality assumption, then you can come to this test. It's a Mann-Whitney test or Wilcoxon rank sum test. Right, there are two group of people invented this method at around the same time. So some people give credit for Mann-Whitney, some people get credit for Wilcoxon. Right, so both are the same tests, although their test statistics look different, but the p-value is exactly the same. They're actually talking about the same thing. Okay, so that's when you have two independent sample situation. What if I have multiple sample, like this 3 sample? Then Tuesday we learned the so-called Kruskal-Wallis test. Okay, so what you do is click Analyze, Non-Parametric Test, choose K independent sample, right? We have more independent sample, more than 2 independent sample, then we do one-way ANOVA. This is also one-way ANOVA, but this is one-way ANOVA non-parametric test, right? Not the F test. So click on that, put in the BMI for test variable and group variable, right? Remember, you click define range, and I actually code these 3 variable, 3 group is 1, 2, 3 here, right? Range from 1 through 3. So I click continue. And Kruskal-Wallis is there. That's test type is check. Just click OK. It'll give you a p-value. This one is easy. There's no one-sided. It's always two-sided test, right? It's always, well, I shouldn't say two-sided test, but this is actually one-sided test, not two-sided test. Always one-sided test. So the p-value is 0.001. So with that, you can draw a conclusion. Significant difference exists among these groups, right? Now, apparently, the third group is significantly larger than group 1 and group 2, right? There's no post-hoc analysis for this in SPSS, so you don't have to worry about that, right? So this is non-parametric one-way ANOVA analysis. Okay. Any question? Okay. I didn't do this one. This one is actually one sample situation. So I have this one sample of BMI, and I want to test whether the average, or actually lean body mass, but similar, right, of this female population is different from 25 or not. So I have one sample of measurement. I want to test the either average or median lean body mass of this sample of the population. Is it significantly different from 25? And I want to do a non-parametric test. Okay, how do we do it? Well, let's create another file. File, new, okay, data. So what you do is just enter these numbers, 26, 38, 26, 21, 22, 32, 32, 27, 31. So you have one sample of measurement, all right? And you want to test whether the the average or the median is significantly different from 25, and we're doing Wilcoxon sign rank test, right? As I mentioned last time, the sign rank test was originally developed for pair sample data, right? So when SPSS designed the system, they actually set it up for pair sample. So in this case, you have to have a paired observation, pairs of observation, and the next value of the second variable will be a variable consists of this test value 25. So if you want to test the average or median of the sample population is different from 25 or not, the first column is your measurement and second column is actually the test value. So I can name this, may call this mu0 maybe, right? And the first variable, call it actually call it lean body mass, right? Lean body mass, maybe, oops. Okay, so I will set up my data this way for non-parametric tests, sign rank tests. Okay, so to run it, just click Analyze, Non-Parametric, Lexi dialog, to related sample, pair sample, right? To related sample, and then mu goes first, lean body mass goes next. I'll take this away, right? So it will use lean body mass minus mu0. Okay, is what Wilcoxon sign rank test is checked. You just click OK. It'll give you a two-sided test. Okay, testing for whether the average lean body mass is significantly different from 25 or not. So this is a two-sided test. Then this p-value it is. That's a p-value 0.109 for testing whether the average BMI for the sample population is different from 25 or not. And this is a non-parametric test now because you use this sign rank test. And you always have to set up your data this way, right? You have a test value, 25, you want to test the average is different from 25 or greater than or less than, right? Of course, this one is different from, so this p-value is the answer. If I'm testing whether the BMI is greater than 25 or not, and that means in this case, actually, that's a one-sided test, right? In this case, if you look at the evidence, you have more positive rank from the difference. And the difference is for lean body mass minus 25. So you have more positive value for lean body mass minus 25. That means what? Most of the lean body mass is greater than 25. So your evidence actually is supporting that the mean body mass is greater than 25. If that's the case, the p-value will be the two-sided p-value divided by 2, right? So it'll be like 0.545 or something like that. Still 0.0545, right? Still greater than 0.05, so you're not going to reject the null hypothesis. I hope I'm making sense, right? So that's what you would do, right, when you try to do a non-parametric test, right, for one sample situation. See the difference between this one and the first one. Let me see. This is a pair sample situation, right? You get these pairs of data in there. If you want to test whether the pair the difference between the pairs is significantly different from 0 or not, you just have the pairs of data in there. You can click Analyze, Non-Parametric, to related sample test, and specify those two values, right? Depends on which one you want to subtract which one. I want to use before minus after, so I let the after go in first before going next, right? This is when you try to see whether the difference is significantly different from 0 or not, right? And this one is applying the pairs, sign rank test. This is sign rank test, right? For pair data, this is sign rank test for one sample. Okay, hopefully you see the difference. And they're both using sign rank test. So sign rank test is good for pair sample situation. It's also good for one sample situation, all right? if you try to deal with this two independent sample, then you should need to use the two independent sample test, which is Wilcoxon rank sum test or Mann-Whitney test. In my lecture note, I use Wilcoxon rank sum test. So make sure you write those things in your note, because I may ask you a question. Just give you a data and ask you what kind of test should I use? What kind of non-parametric test should I use? Should I use sign rank test, or should I use the Wilcoxon rank sum test, right? Or should I use cross-Koalas test? Okay, and you just check the correct method. Okay. Let's see, what else? This is a one-sided test, right? If you want to test whether it's greater than 25 or not, right? And I kind of mentioned that, right? I mentioned that if it's right-sided test, you divide that p-value by 2. Okay. This is a two independent sample test. That's good. This is again a one sample test for proportion. We did that. Right. The last one is chi-square test for independent. I think most of you are good with this, right? Many of you actually, in your project, you actually pick two categorical variables. So when you have data organized in this way, then you want to do a chi-square test for independence. Now this is a situation you have a data organized, right? Otherwise, you're going to have, let me do this. Let me create another new data. Okay. You should have two variables, right? This is maybe population variable. Oops. Yeah, population variable. You also have exercise variable. Okay. So you have population variable and exercise variable. Population, one maybe stay for population A, and then exercise, one may stand for having adequate exercise. So you do 1 and 1, you record one data, right? You could have population 1, population A, and inadequate exercise, you say 2, right? So you enter 2 subjects, right? 2 and 1 and 2 and 2. That means when I do this, I enter 4 cases. 1 is for a person like this, population A and had adequate exercise, okay? The second one is 1 and 2. That means what? Population A and did not have adequate exercise. The third one is population 2B, all right, and adequate exercise. And the fourth one is population B and then inadequate exercise, all right? So I create these 4. Then what I would do is actually do weight cases. I have 110 from that first category, 120 from the second type of subjects, and 180 for this first type of subject, and 320 for the fourth type of subjects. Okay, so I can, if I have data organized in a contingency table, I can create my data like this very quickly by creating a frequency. This one I call it frequency variable, right? So this is the frequency, and I created 4 cases, and I put the frequency for each of those type of outcome, right, on the right of it. And I can click data, weight cases, and check weight cases by, and put the frequency in this frequency variable box. Okay. So if I have that, I click OK. Now this SPSS will consider I have 110 cases of this kind, 190 cases of this kind, and so forth. So if you have this, if you click Analyze, Descriptive Statistic, crosstab, and put the population as row, maybe exercise as a column, and if you click Statistic and do a chi-square test, okay, continue. In doing this, it'll make a contingency table for you and also do the chi-square test for you. So if I click OK, you see that contingency table, 110, 190, 180, 320, exactly that contingency table. It also gives you the chi-square test statistic and the p-value for chi-square test. Right? So this p-value of chi-square test is pretty high, higher than 0.05. So that means what? there's no significant association between population and adequate exercise. Okay. I wonder if you remember this. This is in that chapter for categorical, analysis. This is for testing whether two variables are independent or not. Okay.
Dr. Chang, is this also how you get the confidence interval?
This one only give you the test. Okay. If you want to do confidence interval, you can do this by hand. For instance, if you want to estimate the percent of people who exercise, have adequate exercise, you totally have 290 out of the 800. Okay. So you can actually just do, proportion is 290 divided by 800. Is that what? Hope I copy the right thing. 290 divided by 800. Yeah. Okay. So that would be your proportion. Then you can use this formula again, the confidence interval estimate formula, to get your confidence interval. Am I making sense?
Yeah, so you can't use SPSS to find that?
Now, SPS doesn't give you that option, so unfortunately. I think in the class I mentioned that you can use the confidence interval estimate for mean to kind of approximate this, right? But I guess it would be better off you do this computation. Okay, I think you can do that. That's not a big problem. Okay. So I think many of you would do this eventually, because from my experience, most of the students prefer, or just, when they gather the data, they just gather categorical data. It's easier to gather categorical data than quantitative measurement, right? I know that some of you actually collect data from maybe the bills, the check that you got collected from in a restaurant or something, right? Then that probably be quantitative. Then if you have quantitative variable, then you will do this. And in that case, of course, when you do SPSS, you have quantitative data. In general, you do this explore, all right? When you go through this option, it'll automatically give you the confidence interval estimate for mean, right? If your data is quantitative, you get the I'm sorry. Let me do this. Right. Confidence interval estimate. Let's do this one. This data, let's say before, this is quantitative variable, right? You click Analyze, Descriptive, Explore, put the before in there. Well, difference is good too, right? You want to do the estimation for the difference. It's quantitative measure. You click OK. You remember, these two numbers are the upper bound and lower bound of the confidence interval. And this is the X bar, all right? These 2 points are from X bar minus or plus margin of error to get these 2 points. So if you have these 2 points, find the range, a difference of the two, divide by 2, you get margin of error. Okay. I don't think I have a chance to actually go over the regression, all right? But you did some assignment on regression, so I hope you can review those and also review the lecture videos, right? And the video has examples, and so you can probably review from there. And if you do have any question, like I said, feel free to set up a time to meet with me, right? If you think there are things that you don't quite understand, right, feel free to contact me, right? Don't contact me like a day or two before the exam, right? It'll be too late. And I think I will probably be traveling during that time, right? So you may not be able to reach me like a day or 2 days before the exam, right? So better off if you have questions, ask me earlier, okay? Maybe Tuesday or before Tuesday. Okay, that's the best option. Okay. Any question? Oh, let me see. I have some question from the chat box. Sign tests. Don't worry about sign tests. All right. Sign rank tests will be sign rank tests. Wilcoxon sign rank test and Wilcoxon rank sum test, right? Those are the tests that will be in the exam, right? I think in our lecture note, I think we talked about the sign rank test, right? Then we talked about Wilcoxon. This is a sign rank test, Wilcoxon rank sum. Yes.
When you were doing the confidence interval, you said you had to do it by hand. When you were taking it over the total, were you taking it over the total number of people in the survey or the total number of people that
Yeah, total counts, right? Now let's go back to my notes, right? We totally have 800 people, okay? 290 is from that category that you like to estimate, right? Let me see, let's go back to that table, right? So the category 1, total you have 290. That's out of the 800, okay? So if you want to, this is for estimating the percent of people who exercise regularly, 290, out of the total 800 that you surveyed, okay? Now, if you happen to have more categories, right, like, let me go back. So you have category 1, category 2, category 3. This category had 40, this category had 50, this category had 60, for instance. Total is 150. Then you want to estimate the percentage of people from first category, and that's again p hat is what? 40 out of 150, right? That will be your proportion. Then you use that to this formula to get the confidence interval estimate for proportion. Make sense? In your situation, you probably would be working on doing something like that, unless you categorize your number of time using drug to ever use drug or never use drug, or ever, never, whatever, right? You had used drug or you never used drug, the 2 category. That's kind of simplified your data, right? But it's okay if you want to keep that 5 or 6 category, that's fine. And since you both variable categorical, you can do a chi-square test for independence. And the p-value for that can help you to draw a conclusion about whether there's significant difference in the number of time using drug among these 2 populations. Okay. Sarah asks, is that all we have to know for the exam? Well, like I said, I didn't cover the regression, right? So you should also study the regression, right? Linear regression. Okay. That's almost everything that's going to be covered in the exam. So if you go home and then go over these material again, make sure you can do these, answer these questions. That would be very helpful for preparing your exam. Okay. And again, if you get stuck and there's things that you don't understand, email me, right? We can go over that together. Okay. Okay. Are you going to be here for? No, I'm not going to be there. I'll be doing this remotely. Okay, like what we did last time. Okay. So the format will be similar to what we had last time. Okay. I will upload this recorded lecture. I recorded this, right? So I'll upload that, right? It'll take